Kia ora and welcome to this video on question 1 of the 2017 Scholl Calc exam. This question starts off with part A and B being algebraic, and then part 1C goes into conics, which we're going to look at a little bit more in depth. It's a proof of the reflective property. Okay, so the first question, it's kind of a weird problem. We've got one equation with two unknowns, and we're asked to find all the solutions. So you start off thinking, well, there's an infinite number of solutions. Let's just have a look at the graph. Got x to the 4 minus y squared equals 71. It's kind of hyperbolic. And then apparently there are points that satisfy that equation, so points on the graph that are integers. And they might be hard to find. But oh, there's one. It looks like one. No, maybe not. The answer turns out to be 635. And you can see that it's going through a grid point there. How would you do this problem without a graph? Well, you need to realise that it is just one equation with two unknowns, but the second piece of information is what you need. They're integers. Okay, so if we look at that problem and we recognise the difference of two squares, and we also need to recognise that 71 is prime. So this factors. Normally when we solve problems that involve quadratics, we make it equal 0 first. The reason for that is 0, for something to multiply to make 0, one of the factors would have to be 0. But in this case, it's equal to 71, which is prime, and x and y are integers. And if x and y are integers, then the brackets that I've got here, x squared minus y and x squared plus y, they're also integers. So therefore, so I'm not going to say therefore, what am I saying? Because x and y are integers, x squared minus y and x squared plus y are 2. 71 is prime. Therefore, x squared minus y equals 1, x squared plus y equals 71, 1 times 71, or the other way around. Or you could do the negatives. Turns out two of them don't work. Okay, so if we look at the first possibility, which is the top row, x squared minus y equals 1, x squared plus y equals 71. If we add those two equations, we get 2x squared equals 72, or x is plus or minus 6. If we put plus or minus 6 back into the equation, we find that y has to be equal to 35. If we add the next two equations, we get the same thing for x. X is plus or minus 6, but in this case we say that y is equal to negative 35. Third row, if we add those two equations, we get 2x squared equals negative 72, which doesn't have real solutions. And likewise if we add the last row, 2x squared equals negative 72, no real solutions. Okay, so there's 4 possible answers based on the symmetry of the graph I showed you. We have when x is 6, y is 35, or 6, negative 35, or negative 6, 35, or negative 6, negative 35. Cool. And we've proved it, or we've explained why we've got all of them, because of the fact that 71 was prime. Of course, we could think of 71 having factors 35.5 times 2, but it wasn't possible to have one of the factors 35.5. So we wouldn't get a fraction out of x squared plus y or x squared minus y, if x and y are integers. Okay, second question. We've got an equation. We're told it's got two real roots, equal magnitude, but opposite in sign. So if one of the roots is I don't know, alpha, the other one's minus alpha. Now, because of that, we can really shortcut this problem. A common approach to solve this would be to cross multiply it. I'm not going to. I'll just rewrite the problem out. I'm going to take a little bit of an alternative approach to this. If you want this standard way of solving it, maybe look at the mark schedule. Okay, first up, the quadratic's not in standard format. So what I do is put it into standard format by writing it as 1 over p minus 1 x squared minus b over p minus 1 times x. See, I don't cross multiply, I just split the fraction into two parts, a quadratic part and a linear part. Then with the fraction on the right hand side, I move it to the left by subtraction. Okay, now my quadratic's almost in standard form, I just have to put the x terms together. We know that the solutions are equal magnitude and opposite in sign. What that means is that we have a difference of two squares. I'm going to times everything through by p minus 1 just so that it has a coefficient of 1 in front of x squared. Okay, and if it's a difference of two squares, so it factorizes to x minus alpha and x plus alpha. Okay, we're told that the roots are equal magnitude, opposite in sign. That means that when we expand this, the middle term disappears, becomes x squared minus alpha squared, a difference of two squares. So this middle term we actually know needs to be 0. This dude here must equal 0. Know that the b term, the middle term, put it in inverted commas because there's already b in the problem, equals minus b minus a p minus 1 over p plus 1. We know that that equals 0. Or p minus 1 over p plus 1 equals negative b over a. Okay. Now we also know, being it's a difference of two squares, x squared minus alpha squared, that this last term here must be a positive number. It's got a minus in the front of it, and it's got to be something squared, so that thing must be a positive number. Okay, so we also know that the c, last term, is a negative number because it's already got a minus in front of it. That tells us that c times p minus 1 over p plus 1 must be greater than 0. Can't be equal to 0 because that would be roots of 0. Okay, and notice that the p minus 1 over p plus 1 term from earlier is there. C times minus b over a is greater than 0. That's how we get rid of the p's. we've got minus BC over A is greater than 0. And what are we trying to prove? BC over A is less than 0. Well, I just divide by -1. When I do that, my inequality flips around. And proof. Done. Box. Smiley face. Okay, like I said, I went straight to a difference of 2 squares on that because I used the information in the question to do so. Another way of looking at that would have been to use the sum of the roots and the product of the roots. And if you know about sum and product of the roots, then you could use that. If you don't know about it, then you could look it up. Okay, the third question involves this parabola, and we're asked to show that AC bisects angle BAF. So that, and AC is the tangent. So in other words, this angle theta, and that angle there is also theta. Now that's called the reflective property of the parabola. And what that means is if I have a light at the focus, so imagine that there's a light bulb here at the focus. That when the light goes away from the focus and hits the parabola, it actually reflects off parallel to the axis, and it doesn't matter where you do that. If I hit the parabola there, it's going to reflect off parallel to the axis. And so that's why reflectors are so useful if they're parabolic in nature. You put a light bulb at the focus of the parabola, all of the light is going to bounce off parallel, which makes it useful when you're driving along a road and you want all the light of your light coming from your light bulbs to project out straight. On the flip side of that, if you've got a parabolic satellite dish and you've got signal coming in from a satellite up in the sky, it doesn't matter, the signal, if it's coming in parallel to the x-axis, is going to reflect back through the focus. That's where you put your receiver and your signal all converges to the same spot. And you can assume that the signal's coming in parallel to the x-axis because it's coming from so far away up in the sky that it essentially is parallel. So that's what we're actually proving here. We're proving that the parabola has this reflective property. Okay, so how do we even start this? We've got an equation. Y squared is 4ax, where A is the focus. They don't tell you that in the question. That's something you need to know about basic conics, is that this focus is at the point A. Okay, and we've got another property of conics, is that we've got this line called a directrix. A directrix is a line that's equidistant away from every point. So if I have that point there, I've drawn my directrix clearly in the wrong spot. One sec. Just get rid of that, put it somewhere else. This distance here should be equal to that distance there. I think that the diagram's not to scale, which is off-putting me, but those lengths should be the same. Okay, don't like the diagram, so to teach you a little bit about conics, we're going to go to a diagram that is to scale. I'm going to put in a parabola. Okay, and A is 1 there, and if I type in the focus, of my equation 1, okay, there it is, it's at 1. If I make the slider, if change the slider to 3.2, the focus changes to 3.2. Now if I put this line in called a directrix, of my equation 1, that's a line there that's the same distance away on the other side. It's a vertical line, and if I take a random point on the parabola, that length there, 4.49, is the same as the distance how am I going to do this? Perpendicular line. Same as that distance there, 4.49 for both of them. And if I move that point to somewhere else, of course the distances get longer, but they're still equal. In that case it's 7.16 each. So that's one of the properties. And we were asked to prove that the tangent, so let's put in a tangent, bisects it. Okay, if you look in the mark schedule for this, there is a really shortcut way of solving this problem which uses this property of the directrix. What I suggest you do is to look at that solution and along with this diagram and see if you can understand it. It connects these points here and uses the fact that I've just made an isosceles triangle. Like if I've made an isosceles triangle there, then if we can prove that the tangent bisects that line, then of course the angle up the top will be cut in half. But that's what the proof involves you doing. What I'm going to do is assume that you didn't know anything about directrices. Okay. Just having a little bit of a lag here. Alrighty, so suppose we didn't know that. And we're just going with this diagram here. So we're going to use calculus to find the slope of the tangent. I'll just use implicit differentiation. 2y dy dx is equal to 4a. So dy dx, the slope on the parabola is 4a over 2y, which is 2a over y. And at that particular point where the tangent's drawn, the y value is y naught. So it's 2a over y naught. That's the particular slope there. Okay, so if I found the equation of that tangent, I could use y equals mx plus c, or I could use the y minus y naught equals mx minus x naught equation for a straight line. I've got y minus y naught equals 2a over y naught, that's the slope, x minus x naught. I can find out the point C, that's the x-intercept of that tangent. So I make y 0, making y 0 on this equation I can cross multiply that, I get minus y naught squared, 2a x minus x naught. Now y naught squared is just 4a x naught, because y is on the parabola, and we know that y squared is 4ax. So this is minus 4a x naught. 2ax minus 2ax naught. Remember, I want to find the x value of c there. So if I rearrange this equation, I've got minus 2ax naught equals 2ax. Cancel, cancel. X equals minus x naught. What have I just achieved there? Looking back at the diagram, this position here is x naught. This position here is minus x naught. Okay, that's quite neat. How have I proven that the angles bisect? Okay, well if I call this angle here alpha, then the tan of alpha is y naught, the height, the opposite side, over the adjacent, which is 2x naught. It's a right angle triangle there. Now it's also the slope. It's also the slope 2a over y naught. Okay, so all that proves is y naught squared equals 4ax naught. Okay, so it's a parabola. Brilliant. Haven't really achieved anything there, except this angle here is alpha. Alternate angles on parallel lines are equal. And if I just look at this triangle, well, its height's y naught still, but this length here is x naught minus a, the distance between the foci. So it's y naught over x naught minus a. So if I want to find the length of that, I use Pythagoras. So if you square both those things, FA is y naught squared plus x naught minus a squared square rooted and I know that y naught squared is 4ax naught like earlier, so I get some like terms in there, and that's a perfect square, and therefore the length is x naught plus a. So this length here is x naught plus a. And this length is x naught plus a. I was going to do a trigonometric approach and find the angle alpha, because if I can prove if I can find what that angle is, then I can prove the bisection as well, and prove it's 2. I need to prove it's 2 alpha and use a double angle formula, but I decided against that because I've got an isosceles triangle there, which means that this length is the same as this length, although it's not drawn to scale. And if that's the case, the base angles are the same, which means that's angle alpha, and therefore we've proven that the angles are the same. Done. Now, there are other answers in the marking schedule, but just before you disappear from this video, let's go back to GeoGebra. But this time, let's look at the reflective property of some of the other conic sections while we're at it. Because I guess when you're trying to predict what comes up in a Scholl exam, you got to think, okay, they asked this one year, but what could they ask in future years? How am I going to delete this quickly? Haven't used my iPad in GeoGebra for a while. Should be just a delete thing. Delete for me. Thank you. Brilliant. All gone. Okay, so let's look at an ellipse. So x squared over a squared plus y squared over b squared equals 1. Helps if my equal sign's in the right place. Oh my goodness. No. Oh, we're having a mare here, team. This is where you all fast forward past. We'll just appreciate my fails. B squared. Now, give me an equal sign, please. Equals 1. Righty, it looks like a circle, but of course that's because A and B are the same if I move it round. Okay, I've got an ellipse. See that A is 2.6 is the distance to the vertex, and B is 1, if I make it a little bit more, it's the distance to the y-axis intercepts. If I put the foci in, okay, the ellipse has 2 foci, and like the parabola, if I put a point on the object here, find its tangent, and now consider this line here and this line here, G and H. Notice that G and H there add up to 5.2 and 5.2? Yeah, 5.2, and that's 2 times A. A is 2.6 at the moment, so 2. If I move that point, if H plus G still adds up to 5.2. So the property of the ellipse is that those two lengths, the length between a point on the ellipse and the foci, the sum of the distances is always a constant, and it equals 2A. So if I draw that up the top there, right at the top, and you can see we've made a right angle triangle there, or an isosceles triangle. In that case, H and G are both equal to A. The distance from the center up to the top is B, and then the distance from the origin out to the focal point is usually called C. So we end up with a right angle triangle, C squared plus B squared equals A squared, and that's on the formula sheet. It's a relationship between A, B, and C for an ellipse. Okay, but let's just look at this, these angles here, because this shows us what the reflective property is all about. That angle there is the same as that angle there. And so if you think about basic physics knowledge, the angle of incidence equals the angle of reflection. That's always the case, no matter where you choose. If you're interested in where this appears in real life, Google a whispering gallery. That will give you an example of where someone stands at one of the focal points of a room that's roughly elliptical, works in 3 dimensions. They whisper some message, and then their mate is at the other focal point, and they can hear it loud and clear. Another cool video to watch on YouTube is where it's an elliptical pool table. I think there's a mini golf one as well, where someone start with the ball at one of the focal points, and the hole is at the other focal point, and no matter where you shoot the ball, assuming that everything works perfectly in the collision and the cushions are all nice, the ball will reflect off the cushion and into the hole. So yeah, elliptical pool table is kind of a cool video to watch as well. Now if you want to prove that that's true, it's actually quite a difficult proof, but give it a go, and then Google proving the reflective property of an ellipse, and you'll get some nice maths in there. Similar to what we did, but a lot harder. See you in the next video.